So these are properties of definite integrals. We've been studying the definite integral as a limit, and now these are some basic properties of the definite integral. The first property here, really the property is that the definite integral of 1 from a to b dx equals b minus a. But I wrote it, the way I phrased this, I say the area of a rectangle with height 1 and width b minus a is equal to, and then I have this definite integral equals b minus a. The reason I wrote it that way is because I really want you to think about the picture of this integral. It's not difficult, but it's a kind of a fundamental exercise to always kind of come back to the basics, like what are we really doing with? So here the picture would look like, so let me put in an axis. So here the integrand is the function, is the constant function 1. So here's the function 1. So that's 1. And here we're looking at this function from the interval from a to b. So, this is the part that I want you to interpret. Oh, when we're calculating this integral, I'm trying to now find this area of the region under the curve above x-axis for x between a and b. And here the formula is easy because it's a rectangle. We know it's just height times width. It'll just be 1 times, and the width is b minus a. So that's how we get this result, where we're thinking about it geometrically. If we think about it geometrically, then it's a very easy formula to write down, Because right now, we don't have we're pretending that there's no connection between antiderivatives and integrals, but that'll end very soon. The second property is just basically a property of sigma notation, because a definite integral is a special type of sigma notation. It just says the definite integral of the sum or difference is the sum or difference of a definite integral. The third property here is, again, a property of sigma notation. Basically, it's the property that allows us to pull out the constant. So here, the definite integral of a constant times a function is the same as the constant times the definite integral of the function. So this is an interesting property. The way we think of it is that we're reversing direction. So what do I mean by that? Here on the left-hand side, I'm integrating from a to b. On the right-hand side, however, I'm integrating from b to a. And so we've reversed the order of integration. That's what I mean by reverse direction. We've reversed the order of integration. And when we do that, you get a minus sign. So why is this true? I think it's important for us to not be tricked by the notation. So here, when you look at this definite integral, I want you to think, oh, this looks like limit as n goes to infinity of sigma I going from 1 to n, f of x sub I star times delta x, where here, we're told the way you calculate delta x is I'm going to take the top bound, subtract the bottom bound, and divide by n. So here, delta x will be b minus a over n. And so now I want to compare with the other side. On the other side, start with just the integral. Forget the minus sign that's over there. Just start with just the integral. For this integral, again, when you think about, okay, what does this integral really mean? It's going to be basically the same as what's on the left-hand side. It's the limit as n goes to infinity of f of x sub I star delta x. However, here, delta x will be calculated. Again, we're using the same formula. You take the top bound minus the bottom bound. Here, this will be a minus b over n. And you can see it's different. It differs from the delta x on the left-hand side by a minus sign. So if I now multiply in a minus sign to this Riemann sum on the right-hand side, that'll make the Riemann sum on the right-hand side, it'll make the delta x on the right-hand side look like the delta x on the left-hand side, and we'll get the same Riemann sum. So yeah, that's what that's saying. At the end of the day, what you should really just see is, oh, if I switch the bounds, then we're gonna have to slap on a minus sign. So you switch the bounds, a minus sign, appears in front of the integral. So here, this is sort of a tricky property. It says you can integrate this integral from a to b. Instead of just going a to b, you could kind of break your journey halfway, or not necessarily halfway, but you can break your journey in between. So for example, the integral from a to b of f of x would be the same as the integral from a to c, and then plus c to b. And so if you follow the journey, we've done a to b, but we had a little, side route here where we went through c. Instead of just going a to b, we went a to c and then c to b. And I say this is tricky because the number c does not have to be in between a and b. Let me draw a picture here. So here's my axis, and let me draw, so let me make 3 marks here. And so the reason I say this is tricky, so I'll call this A, I'll call this B, and I'll call this C. So here you see C is outside. It's to the right of B. So here's our function, f of x. And so what the integral is saying is, we can calculate this area if we do the following integral, if I do integral from a to c, right? So that's this integral right here. And so that'll calculate all this stuff. And then I'm going to do integral c to b. And that's this integral. When I do c to b, this integral will be negative. Here we've reversed directions. Here the bottom bound, when I go c to b, is bigger than the upper bound. And so here, this integral, when you go from c to b, will actually subtract this section off. And you see what we're left with is our original integral a to b. So that's why I say it's a little tricky, because the c does not have to be in between a and b. Here we say this is true for any constant c, whether it's in between a and b or whether it's not. So yeah, I'll let you think about that. And something like this is useful for when we're trying to integrate, for example, something like the absolute value function or a piecewise defined function, where the function changes its definition across its domain. And I'll show you an example of that in a second. The sixth property says if f is greater than g, then the integral of f will be greater than the integral of g. And here, the easiest thing here, again, is to think about the picture. So suppose I have a function f of x, suppose I have a function f of x. So here's my a to b. And so this is the function f. And now suppose I have a function g of x that's less than f. So when we integrate, what we're saying is that this area under f, so that's the integral of f, going from a to b, is obviously going to be greater than this area, which is the integral of g going from a to b. And so if you think about it in terms of pictures, it kind of makes sense. It makes a lot of sense, and it's, to me, I don't want to necessarily just memorize the formula. It should kind of somehow have some meaning, and then I'll memorize it. So here, if you think about the pictures, these things do make sense. And the last one is very similar to number 6. It says if f of x is between two numbers, little m and capital M. So little m would be the lower bound and capital M would be the upper bound. They're both constants. Then the integral of f from a to b will be bigger than little m times b minus a and capital M times b minus a. Again, the formulas kind of look mysterious, but really if you draw the picture, it's not that bad. So here, what we have here are two constants. So here is my constant capital M. So that's capital M, capital. And then here is my constant little m. Oops, that should be a straight line. Try that again. Here's little m. So let me label it. Oh, it's not very straight, is it? All right, last time. Okay, little m, let me label that. Now, here is the function f that's in between capital M and little m. And here's my a to b. And so now what we're doing is we're comparing, so the integral of the function f of x dx, the integral of f from a to b is this area. The integral of little m, if we integrate this function, the area will be m, little m times b minus a. This area down here is exactly where this term is coming from. And if you integrate capital M, that'll give us this area under the curve here, under capital M. And that's exactly, the area of capital M here. This is exactly where this term is coming from. Because the area of this rectangle now is the height, which is capital, times the width, which is b minus a. And you're comparing it to the area under the curve, which is this area under the red region. And so if you think about it geometrically, these things do make sense. They're a little less mysterious. Of course, at the end of the day, I'm going to ask you to memorize them. So here's a quick example just to show you how we might use some of these properties. So here, in this case, we're given an integral that we actually do not know how to integrate. We do not necessarily know what the antiderivative of 1 over the positive square root of x squared plus 7 is. And actually, we won't learn how to do this integral in this class. So this integral, you will learn how to do this integral in Calc 2, okay? But it doesn't matter. Even though we can't do the integral, we can use properties of the integral to find bounds. I can tell you how small the integral could possibly be and how large the integral could possibly be. So here we're told to show that the definite integral is going to be greater than root 2 over 4 and less than 1/2. Okay, so the starting point of this problem, the only information we know is that x is between 3 and 5, and that our integrand is this function, 1 over the square root of x squared plus 7. And so that's all we'll need. We'll just use now the properties to solve this problem. So starting with what we're given, what I want to do now is build up to my integrand. So here, this x, I want to now manipulate it so that it ends up looking like 1 over the positive square root of x squared plus 7. So the first thing I'm going to do is square everything. And here, the inequality doesn't change directions because, if you look at the squaring function is an increasing function for x greater than 0. Now I'm going to add 7 to everything. 9 plus 7 is 16. X squared plus 7 is right here in the middle. And then 25 plus 7, if I'm not mistaken, is 32. Now I need the root. I'm missing the square root. So let me go ahead and take the square root of everything. And remember, the square root's an increasing function. So if a is less than b, then the square root of a is less than the square root of b. So I don't have to change the direction of the inequalities. And here now remember, square root of 16, positive square root of 16 is 4. And here positive square root of 32, 32 is 16 times 2. So this will be 4 root 2. So here's where I'm at this stage, that I know the positive square root of x squared plus 7 is bound below by 4 and bound above by 4 root 2. The last thing I need to do is to take a reciprocal. So don't forget here, you know, the x squared plus 7 needs to be in the denominator. Now, when I take the reciprocal, the inequalities flip around. Because 1 over x is a decreasing function. So that means if a is less than b, then 1 over a will be greater than 1 over b. So finally now, since, you know, I can use the property of integrals. The property of integrals says if this integrand is between little m and capital M, I can now just slap on integrals and integrate, in this case, from 3 to 5. You can just slap on integrals everywhere here, on the left side, the middle expression, and on the right side here. And now I'm going to calculate these derivatives that are at the, these integrals that are at the end here, these two. And I'll show you that we will get these constants. That's where these bounds are coming from when I calculate the integrals. So for this first integral, we're just using that property. First, I'm going to take the constant and pull it out. So there's the constant. Then we're integrating 1 dx from 3 to 5. That's just the area of a rectangle of height 1 and width 5 minus 3. And so that's where I'm getting 5 minus 3 times the constant we pulled out. So we get it's equal to 2 over 4 root 2. And now if I rationalize the denominator, if I multiply top and bottom by root 2, here, root 2 times root 2, this becomes a 2 right here in the denominator. That becomes a 2, which I can cancel with the 2 in the numerator. And then all I'm left with is root 2 on top and a 4 on the bottom. So after rationalizing the denominator, I get the integral is root 2 over 4. And the other integral is basically the same idea. I pull out the 1/4, then the integral of 1 dx from 3 to 5 is just, 5 minus 3 times 1. It's just the area of a rectangle of height 1 and width 5 minus 3. So here I get 2/4 or 1/2. And so I can just replace this integral with its value, which was root 2 over 4. And I can replace this integral at the end here with its value, which is 1/2. And so we get our conclusion here. So there's the 1/2. And there's the root 2 over 4. So this example was really designed just to show you an example where we're practicing manipulating the inequalities. We're very used to working with equalities, but more and more as you move up, we're going to have to do more work with inequalities. So I really wanted to do an example here to show you how we can use inequalities to find lower and upper bounds for a definite integral. This last example here, I just wanted to do one final, let me set up. Whoops, sorry, I got accidentally muted. This last problem, I want to now do one final example where we set up the limit definition of an integral. So here it says set up, but do not evaluate a limit of Riemann sums to evaluate, to find the integral of 3x cubed from 1 to 2 dx using a regular partition and midpoints. So here, the first thing that I realize or I say here is that in this problem, we're trying to find the exact value of the integral using a limit definition. So what that means is the number of subintervals that we use will just be n, the letter n. And at the very end, the last step, I'm going to send n to infinity. Okay, but the rest of it starts out the same way. Whether I'm approximating or finding the exact area, I need to identify the function f of x, which is 3x cubed here, and the interval a to b, which is 1 to 2, because I'm interpreting the given integral as the integral a to b of f of x dx. So I can extract the function and interval from that information. And then keeping in mind that n is just going to be the letter n, I can calculate delta x. Remember here, the regular partition means that the subintervals have to be equal length. So I just do b minus a, divide it into n equal pieces, where n stays as the letter n. Okay, that's like one of the big differences between approximating the area and finding the exact value. So once I have delta x, I can calculate x sub I. You remember the x sub i's are like mile markers. After you travel a distance of delta x on the x-axis, you'll see an x sub I. So after I travel one distance of delta x, I'll see x sub 1. After I travel two distances of delta x, I'll see x sub 2. So this gives us our generic formula for how you can find the x sub I. So here a is 1, delta x is 1 over n, so x sub I looks like 1 plus I over n, I from 1 to n. You know, if you plug in I equal to 1, that'll be our right endpoint of the first subinterval, you know, so on and so forth. If you plug in I equal to 2, that'll be the right endpoint of the second subinterval. And so even though we're asked to do midpoints in this problem, I always first find the formula for x sub I. Whether we're asked to use left endpoints or midpoints or right endpoints, we always find the formula for x sub I, because once I have the formula for x sub I know the formula for x sub anything. So here, the sample point we want to use, x sub I star, is to be the midpoint, which is x sub I bar, which in terms of our partition is just the average of the endpoints of our ith subinterval. So x sub I minus 1 plus x sub I divided by 2. So now for the formula for x sub I minus 1, I'm just going to take the formula for x sub I and replace the I with an I minus 1 wherever it occurs. So this is the formula for x sub I minus 1. It's 1 plus, and then I put an I minus 1 over n. It's the same formula here. X sub blah equals 1 plus blah over n. So x sub I minus 1 will equal 1 plus I minus 1 over n. And then x sub I is, you know, I just copy that down. There's no issue there. X sub I is right here. And now I do the math. I'm just adding here. I'm adding 1 plus 1, and I'm adding the fractions. So I get 1/2 on the outside. When you add, you get 2 plus, when you add the fractions, I minus 1 plus I is 2I minus 1 divided by n. And then when I distribute the 1/2, here I get my formula for the midpoint. This is what I'm going to plug into my function, and that y value is going to be my approximation of the height times delta x, which is the width. That'll give me my area. So here's my limit definition of the integral. Here's my limit definition of the integral. We said that the sample point that we're using should be the midpoint. So I replaced the x sub I star with the notation for the midpoint, you know, just to practice the notation. But I know this midpoint we calculated has this formula. So I end up replacing the x sub I bar with that midpoint in the function. And here, you know, you should tell yourself the story. What you should see here is this is the height using the midpoint of the ith subinterval times the width. That gives me the area of the ith subrectangle. Let me add them all up. This gives me an approximation. And now let me send n to infinity. So now we're using infinitely many rectangles. That'll give me the exact value. So the last step here is I just replaced f of 1 plus 2i minus 1 over 2n with the actual function value. So here, remember, f is this function here, 3x cubed. So I have 3 midpoint cubed, and then times the delta x is my 1 over n. So this integral, in terms of writing it as a limit of Riemann sums, would look like that. And the question also asked, will this limit exist? So we had a theorem that said if the function we're integrating is continuous, then the limit will exist. So here I said the limit will exist because f of x equal to 3x cubed is continuous. And so it's integrable. So integrable is another way of saying that the limit definition of the integral for a particular function will exist. So yeah, this is, a good problem in terms of practicing the notation and how to set up the limit. To actually evaluate the limit, this is quite a terrible problem because now you have to cube this whole thing and then, deal with all that. Distribute the sum after you cube it, pull out anything that's not a letter I, pull out all the constants and all the letter n's out, and then get rid of the sums using the formulas for the sums. So it's definitely not an enjoyable problem to do the long way, the quote unquote long way. So that implies there's a short way. So yes, let me now show you the beginning of the fundamental theorem of calculus, which makes it so that we can calculate definite integrals without doing this limit definition stuff, which, as you know, is quite tedious. So this is called the evaluation theorem. I like to also think of it as the mean value theorem strikes back. So you remember when we studied the mean value theorem, this right here is the real reason we studied the mean value theorem. So the evaluation theorem is also known as the fundamental theorem of calculus part 2. So we're starting with the fundamental theorem of calculus, FTOC part 2, and then we'll talk about the fundamental theorem of calculus part 1. It's kind of like the prequel. So here, the evaluation theorem says, if f of x is continuous on the closed interval, this interval can also be an open interval. Okay, it doesn't have to be closed. And if capital F of x is an antiderivative of little f of x, that is if capital F prime equals little f, then the definite integral of little f, which we can write with this integral symbol, will equal f of b minus f of a. So I also wrote it in words up here. The definite integral of f of x over the interval converges to f of b minus f of a, or, in notation, basically, this is the important part. And what you should see here, what this is helping us, how this is helpful is we no longer have to calculate the integral using the limit definition. So now, if we know the antiderivative, we can skip the Riemann sums. So let me very quickly show you the idea of the proof, not the proof, but just the idea of the proof. I want you to see where the mean value theorem comes into play. So suppose capital F is continuous on the closed and differentiable on the open interval. Then by the mean value theorem, we know there exists a point C in the interval such that F prime, capital F prime of C equals capital F of B minus capital F of A over B minus A. So now what I'm going to do is I'm going to move this B minus A to the other side. And so we get F prime of C times B minus A equals F of B minus F of A. So the F of B minus F of A, that's already starting to look like the right-hand side of our evaluation theorem. Okay, so now let's connect this up to the integral. So remember here, capital F is assumed to be an antiderivative of little f. So remember that capital F prime equals little f. Okay, that's what we're assuming here in this theorem. And so now let's approximate the integral a to b little f of x dx. And for the sake of this proof, so that it's kind of easier to see what's going on and for me not to use too much notation, I'm going to use one subinterval, right? Generally, that's not a great idea, but for the sake of this proof, it'll make it easier to understand. So I'm using n equal to 1, which means what? We only have one subinterval, x sub 0 to x1, that equals our interval, closed interval a to b. So then here, the length would be b minus a divided by 1, right? N is 1. Typically, it's delta x equals b minus a over n. Here, n is 1. And now I need to pick a point. Remember, if you look at our limit definition, I need to calculate the height. I approximate the height by randomly picking an x value from the ith subinterval and evaluating the function there, using the y value at this randomly chosen point in the interval. What I now suggest is, hey, look, the mean value theorem gave us a number c in the interval. So c happens to be in our subinterval. So let's choose the x sub I star the sample point from this subinterval, let's choose it to be the number c that we get from the mean value theorem. So now my approximation becomes the integral. I'm going to approximate with height times width. The height at x sub 1 star times the width is delta x, but x sub 1 star, we said, use that number c that you get from the mean value theorem. Now remember, little f of c is going to equal capital F prime of c. So I can replace this little f of c with capital F prime of c. And then the b minus a was the width of the delta x. But now look what happens. The mean value theorem exactly now says this thing, capital F prime of c times b minus a, equals f of b minus f of a. And so I can replace that by the mean value theorem with f of b minus f of a. So now if you look at the ends of the equation here, at the very left end, I have a definite integral. And at the very right end, I have the approximation of that definite integral. So using the mean value theorem, we're able to prove that the definite integral of f from a to b is approximately, you know, the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a. And here, this is just an approximation because we used one subrectangle. But if I use n of them and send n to infinity, we can show that approximation becomes an equality. And so that proof, the full proof is in the textbook if you want to look at it. It's kind of complicated because there's a lot of notation. So I wanted to do this one subinterval version where you can kind of see the connection between mean value theorem and the limit definition. The connection is right here. That when we make our partition into the n subintervals, for each subinterval, apply the mean value theorem. It'll give you a number c. Use that number c as your x sub I star. We do this, we apply the mean value theorem for each one of the n subintervals. You know, here I just had one subinterval, but if I had two, I'd apply mean value theorem separately to both the subintervals. So anyway, in this way, we can use mean value theorem to find the shortcut formula for calculating definite integrals. This is instead of doing this limit of Riemann sums. So I wanted to just summarize all the results about antiderivatives. So this is the slide on antiderivatives. And now I want you to think about, how does this symbol here, the integral symbol without bounds, without numbers, this is also known as an antiderivative or an indefinite integral. How does that differ from the definite integral? So one thing you should always remember, a definite integral is going to equal a number. A definite integral is a net area. An antiderivative is a function, okay? But we can use the antiderivative to evaluate the definite integral. So here I wanted to kind of connect the two ideas. The idea of the definite integral, the limit of Riemann sums, and the idea of antiderivatives, they get connected right here. So all the properties are the same. There's nothing different here. You know, the antiderivative of 1 is x plus c. Remember how we can verify this? Take the derivative of x plus c and you get back 1. Here, the derivative of a constant, you can pull out the constant, you know, and take the derivative. Here we have the power rule. So here's the one I've added at the very bottom here. So we have the antiderivative formula for cosine and sine. We have the fact that the antiderivative of the sum is the sum of the antiderivatives, and you can pull the constant out here. Here's the new one that I've added. If f of x is continuous on the closed interval, then the definite integral. So this thing, you should think that's the limit as n goes to infinity of sigma I going from 1 to n, f of x of I star delta x. The definite integral, the net area, is equal to, now look at the notation here very carefully on the right-hand side. The integral without the bounds, this part, this is referring to this function right here. That's the antiderivative. The integral without the bounds, that's an indefinite integral or an antiderivative. And so I'm replacing that antiderivative with the actual, you know, what is the antiderivative when I actually work it out. and then you do f of b minus f of a, and you actually do the math, the constants cancel, I'll show you, and you get our final value here. So I wanted to show you this notation and to have you kind of think about what's on the left side here of the equal symbol, what's on the right side, and how are they different? And I'm going to let you think about that. So now let's do some actual problems. So this is not a difficult problem, but we have done this definite integral with the limit definition. So I wanted to verify that we get the same answer. So here, I just need to find an antiderivative of x squared. We know that 1/3 x cubed plus c is the most general antiderivative of x squared, and we can check it. The derivative of 1/3 x cubed plus c will be x squared. So now I can use evaluation theorem. The definite integral of x squared from 0 to 5 will be the antiderivative of x squared, where I evaluated at 5 minus the antiderivative evaluated at 0. You can see that the plus c will cancel in a definite integral. So when we're doing a definite integral, when we're doing an integral with bounds, it's not necessary to write the plus c. It's not wrong to write the plus c. If you write the plus c, you'll be fine, but it's not necessary because the plus c will cancel out when you do the f of b minus f of a part. Okay, so when I'm doing a definite integral, typically I'll skip, I won't write down the plus c, but if it's a antiderivative or indefinite integral, an integral without bounds. So here I removed the bounds up here. For this, yeah, I'm going to want to write 1/3 x cubed plus c for an indefinite integral or antiderivative. Okay, for the definite integral, it's really not necessary because it'll cancel. So this next example is not difficult, but there's a mistake here that's very common that very many students make. So here, this is the definite integral from 0 to 2 of x times 2 plus x to the 5th. So the big mistake I see here is students think that the integral of the product is equal to the product of the integrals. So what I'm saying is here, we cannot split up the integral. In general, it's not true that the definite integral of f times g equals the definite integral of f times the definite integral of g. The integral of the product is not necessarily equal to the product of the integrals, okay? So here in this particular case, I can't solve this by just saying, oh, let me integrate x first by itself, and then let me integrate 2 plus x to the 5th by itself and multiply the two. That's definitely a very easy thing to do, but it's also a very wrong thing to do. And sometimes I've seen students where they do that the whole test, and there's nothing I can do at that point. For this integral, what we need to do is to simplify the integrand. I hope your algebra vision told you that, hey, there's still math to be done here. This x can be distributed. So x times 2 gives me 2x. X times x to the 5th gives me x to the 6th. Now I can integrate this. I can find the antiderivative either term by term or just do it all at once. The antiderivative of 2x is x squared. According to power rule, antiderivative of x to the 6 is x to the 7 over 7. And then we apply the bounds. I'm going to plug in the 2 minus the same function where I plug in the 0. Minus the same function where I plug in the 0. But I didn't actually write out the plugging in the 0 part because I noticed that it's just 0 because every variable gets replaced with a 0 and you just get your, you do f of b minus f of a, the f of a part is just 0. So I didn't even write it down at all. I just have the integrand, the antiderivative evaluated at 2. And then I just did the arithmetic, I just figured out what 2 to the squared and 2 to the 7th were, and I added those two and completed the fraction there. So yeah, here, let me just warn you, please be careful of this. Like I said, it's a very natural mistake to make. I get it, it's a very natural mistake to make, but still a mistake nonetheless. we never had as a property that, integral f times g equals integral f times integral g. Okay, so here I want to do an example with trig functions. And again, here, this is a product, and we have to resist the urge to try and say, okay, let me do integral of secant times the integral of tangent. So here we want to try and, one way to do these is just to ask yourself, do I just know the antiderivative? Can I guess the antiderivative? So here, if we go through our trig derivatives, we'll realize that the derivative of secant is secant tan. So secant is an antiderivative of secant tan. So by the evaluation theorem or fundamental theorem of calculus part 2, I can say this antiderivative of secant tan from pi over 4 to pi over 3 is just secant evaluated pi over 3 minus secant evaluated at pi over 4. And then, I did my unit circle and figured out that that looks like 2 minus root 2. So this one wasn't difficult, but, don't try to integrate this like by trying to integrate secant and then integrate tangent and then multiply those two. That's, that's just something to avoid and be very careful with. So you know me, I'm obsessed with absolute values. So of course I have to do and evaluate the definite integral of an absolute value function. So here I really want to warn you again. Sometimes I'll see students do wild stuff, like they'll leave the absolute value in there and then just try to integrate inside the absolute value. No one said that that we could do this. Nowhere in the book is it written that this is an okay move to do. And therefore, we must resist the urge to invent mathematics, just to make up stuff, okay? Here, what we should really do is go back to basics. We ask ourselves, what exactly does this mean? What exactly does the absolute value of x plus 1 mean? And so I'm going all the way back to basics. Here, I wrote down the definition. Remember, the absolute value of a equals a if a is greater than or equal to 0, and equals negative a if a is less than 0, where here a is x plus 1. So I write down the definition of the absolute value, and then I just move the plus 1 over here just to isolate the x's. So here's my function, and here's what the graph looks like. How did I figure out the graph? It's really easy. Graph the thing in between the absolute value bar. So here's the graph of absolute value of x plus 1, and then take anything that's below the x-axis and reflect it above the x-axis. So I take this section that's below and reflect it above the x-axis. So you get the graph of absolute value of x plus 1. And so when I look at this, you see when I integrate from -2 to -1, the function I'm integrating is negative x minus 1. However, when I integrate from -1 to 1, the function I'm integrating is x plus 1. What that means is I have to break up the domain of the integral. This integral that's going from -2 to 1, I need to break that up. I need to go from -2 to -1, which is this section, -2 to -1. And I'm going to integrate this function in that section. And then I'm going to integrate from 1 here, sorry, -1 to 1. And from -1 to 1, the function looks like this, x plus 1. So here, integrate -1 to 1, replace the absolute value with its definition when x is greater than -1. And when x is greater than -1, the absolute value of x plus 1 just looks like x plus 1. Now find the so now we do each of these integrals separately. So here, I find the antiderivative here, and then do the second integral, find the antiderivatives, and then we do f of b minus f of a for each term separately, f of b minus f of a. And so when I did that, I got this for the first one, this for the second one, and then you combine everything, and I get the answer here is 5/2. And when you're integrating an absolute value, then you can definitely say this is an area. This is not just a net area, this is a flat out area, because the absolute value function is always greater than or equal to 0. So yeah, that was the absolute value function type problem that I wanted to show you. Or if you're doing a piecewise defined function, you do it this way. We need one integral for every time the integrand changes, every time the function we're integrating changes. So here, this function required one integral, and then this function here required a second integral. So that's what we see here. Here's the integral for that function, and here's the integral for that other piece. So when your function definition changes, you got to use a different integral. I can't use one integral to somehow get two functions. So let me just talk about the interpretation here. What does it actually mean? So the integral of a rate of change is interpreted as a net change. So for example, if the thing we're integrating, little f of x, has an antiderivative capital F, then the integral of little f will equal f of b minus f of a, and this is interpreted as the net change in f of x from b to a. So what does that mean? Well, at one point, here's f of a, and here's and I think of f of a sort of as a starting value, and here's f of b, and so now when I do f of b minus f of a, we're calculating this difference, and that's what's thought of as the net change in capital F over the interval a to b. And this could be negative, right? F of b could have decreased. F of b could be down here. And now when I do f of b minus f of a, it'll be negative. But that's still interpreted as the net change in capital F. Like its starting point was f of a and its end point was f of b. And so you take the difference and you kind of know the net change from that starting point to the end point. So there's applications to this that we've already seen. For example, if v of t is the velocity, then we know velocity is the derivative of the position function. So when we integrate the velocity, we're integrating the derivative of the position function, we're getting s of b minus s of a. So look, this is literally, if you think of s of a as your starting position and s of b as your ending position, this is what we would have defined as our displacement. It's the net change in distance, or what's known as displacement. It's not the total distance we've traveled, it's just from my starting point to my ending point, how much distance did I move? And if we integrate the absolute value of the velocity, this will give us the total distance, because in this case, the absolute value is always positive. So now we're dealing with something that's always moving to the right. There's no, when you just talk about v of t by itself, this could be positive or negative. And so the particle could move to the right and then move to the left and then move to the right. And this wouldn't calculate that overlap. But when we put in an absolute value, it can only move to the right and it'll never overlap. So here, when we calculate the integral of the absolute value, this will give us the total distance in this case, as opposed to the displacement. And we had solved displacement and total distance problems in chapter 2 without using an integral, really doing it the hard way. So one huge application, and I'll stop right after this, is the application to density. Okay, so density, I'm sure you know from your physics class, density is basically mass per length. That would be one-dimensional density. In 2D, density would be mass per area. In 3D, it's mass per volume. This is a huge application in Calc 2, Calc 3, and in engineering in general. So if we have the density function and we integrate the density where x represents your length along the x-axis, your position on the x-axis, the integral a to b f of x dx will be the mass of the rod between x equal to a and x equal to b. And so here's what I wanted to show you. How do I know it's the mass? So here's what I want to show you is to do some, what I call unit analysis. Here, the f of x function, its units are mass per length because it's the density function. And here dx, this is on your x-axis. So the units of dx is length. And now when I do mass per length times length, obviously the length cancels. And so that's how I know this is integrating to mass. you know, the unit analysis is really helpful. Like for example, here, this would be like miles, miles per hour. And here t is time. So that's hour. And you can cancel. You see the units of this integral is miles. So that helps me understand what the integral is doing. Okay, so that's what I wanted to show you, to kind of do the unit analysis here. So think of the units of f here, be mass per length. The unit of dx here, this is the unit of the x-axis, which is length. And now if you multiply this, the length cancels. That's how I know this integral will give me the mass. All right, everybody, I'm going to stop right here since this is my time.